and show you a little couple of examples. Then you'll have this, and if you want to, like I said, folks on this side of the room, finish up your lab from yesterday. I can give you credit for that when you get it. So different different things are going to heat up differently based upon their material. Okay, if you want to, and we all know this because if you a couple weeks ago was the first kind of warm, really warm day, really 92 degrees last week, and I got home and it's 92 degrees and I've been playing tennis. My first instinct is I want to jump in this pool in the backyard because I put the pool up a couple weeks ago and I got the pool there ready to rock and roll. Now, how do you think it felt when I jumped in that pool? Oh. Holy mackerel. The air was 92 degrees, but that pool was still probably 60. It was freezing in that pool. Okay, so why?
Because it takes longer for water to heat up.
Very good. Because water has a greater specific heat than air. It takes more energy to heat up water than it does to heat up air. Okay, you guys know this because, and same thing with cooking something on the stove. If you put a pot on the stove and the whole pot is there touching the stove, are you going to grab the wooden handle or the metal pot? Why?
The pot heats up faster.
Very good. The wood has a very high specific heat. It takes a long time for the temperature to change on that wood, whereas the metal has a pretty low specific heat. Just a little bit of heat change is going to make that metal change really fast. Same thing when you take it off the heat. The metal is going to cool down really fast. It doesn't take long to change the temperature of metal. It takes a long time to change the temperature of something like wood or rubber or plastic. Does that make sense? Now, when you're changing the temperature, when you're making something hotter, what are you actually doing? What are you actually doing physically with the atoms and the molecules? Put them together? No. What are atoms and molecules doing when they get hotter? They're moving faster. So things like metals and air, it's easier to speed the molecules up and then slow the molecules down. Things like water and wood, it's harder to speed the molecules up, but then it's also harder to slow the molecules back down. You're not going to pick up a burning piece of wood even after you put the fire out because it takes a long time for that piece of wood to cool off. Make sense? All right, so let's add some math to this. Yesterday we have our two formulas. They're up here on the board. We're just going to add formulas to this each day. Today's formula is the specific heat formula. Q represents our heat energy. And does anybody remember the unit? We didn't really talk about it that much yesterday because we kind of did it fast and I didn't really mention it in class, but maybe on your worksheet you figured it out. The unit for energy. I wrote it down at the end. It's called joules. Heat energy is measured in joules. It looks like jowls, but it's pronounced joules. Okay? It's big J. Okay? Now, heat energy is going to be equal to your mass of whatever you're measuring in grams times the specific heat, where the specific heat is CP usually is what it is. Specific heat is a constant number. This is the amount of heat, this is the energy it takes to raise whatever you're working on by 1 degree if you have 1 gram. So specific heat is the amount of energy it takes to raise whatever by 1 degree for 1 gram. Lunch. For you, buddy. All right. So specific heat is different for every substance. So it's going to be unique for every material. So I'm gonna have to either give you that number or you're gonna have to find that number for the specific heat. And then the last thing we have is delta T. Now, delta, that symbol, that triangle symbol, used in math class to mean triangle, but in chemistry class, anytime you write a triangle, does anybody know what it means? Anytime you write a triangle in chemistry class, let's think about what we need to do here. That's our energy, that's our mass, that's our specific heat. T, you could probably tell me what it is. Temperature. What are we trying to do to the temperature? If I want to heat something up, what am I doing to the temperature? If I heat something up, what am I doing to the temperature? Guys, I'm not being complicated. If you heat something up, what are you doing to the temperature? You're making it change. You're making it go up. So that triangle there just means to change. The change in the temperature. Now, most of the time, when I'm talking about temperature, I want to see temperature in what? This is huge.
Celsius.
Not Celsius.
Kelvin.
Kelvin, because remember, Celsius is a degree measurement. But let's look at an example of that. If we heated something up, the temperature went from 20 degrees Celsius to 100 degrees Celsius. What's my delta T? What's my delta T? Guys, y'all think I'm such a hard teacher. This is I'm asking you a really, really simple question here. If I went from 20 degrees to 100 degrees, what is my change in temperature? 80 degrees. Come on, guys. Wednesday, we should be bit into it by now. Okay? 80 degrees is my delta T. Now, if I change that to Kelvin, what are we going to do? Just add what number? 273. So we have 293 K to 373 K. What's my delta T? What's my change in temperature? You don't need a calculator. Thank you. Okay. My delta T is the same or different between those two? It's the same. So I know I always make this rule that you have to use Kelvin. But if I'm looking at the change between two, it's going to be the same whether you're talking Celsius or Kelvin. Does that make sense? You know what it is? Okay, so I'm not going to say you have to use Kelvin here. I just want to know the change. Now, what if my temperature goes down? What's my change going to be? Okay, I agree, except for one problem. If I went from 100 to 20, my change would be 80, but it would be negative 80. And so adding a negative sign to that would just make my answer negative, which means instead of gaining energy, I rock and roll. Ready to kick some tires, light some fires on this? It's not that hard. It's plugging and playing. Ready to roll? Yes, sir.
How did you get 80?
20, 100. How'd you get 80? Sure. I mean, subtract, look at it. What's the difference? You with me? All right. So let's do some examples. I'm gonna throw a simple version of this up over here on the board so that we can know what I mean. We have Q, which is energy in joules. We have M, which is going to be grams. We have CP, which is going to be specific heat. And delta T, which is our change in temp. All right, so let's look at the beginning and the end. I usually like doing that. Let's look at number 1 and number 8. All right, so number 1 says we got a 15.75 gram piece of iron. It absorbs 1,086.75 joules of heat energy. Need one bit? You got it. And its temperature changes from 25 degrees to 175 degrees. Calculate the specific heat capacity of iron. All right? Do I have a cube?
Yep.
What is it?
100.
Look again.
1,000.
Keep talking.
86.75.
Do I have an M?
Yep.
What is it?
15.75.
15.75. Do I have a CP? Do I have a specific heat? So right there on that front corner, sweetheart.
No.
Very good. That's what I'm looking for. That's what it wants to know.
Yes.
Thank you. Okay. And then do I have a change in temperature? How much?
25.
150. From 25 to 175 is going to be 150. Just that front corner is all you need, sweetheart. 150. Can I math this up?
Yes.
What we're going to do first? Multiply them two things. And then whatever we get, we're going to take that divided by whatever we got. Wait. This divided by that times that. But make sure you do your multiplying first. Got a vote for 2.1739, but let's make sure everybody agrees.
I got something different.
What'd you get?
1.71.
Well, what'd you do?
I did
Read the calculator screen.
1086.75 times 50.
Whoa, times? What did we say we need to do with that number? It's on the other side. I mean, like, dude, you can do the math. Here, watch. Okay, so multiply this guy and this guy. So we end up with 15.75 times 150. And then we're going to say that divided by whatever that is. So 1086.75 divided by 15.75 times 150. That should equal that, unless today's is lying to. I heard of Mr. Tyler over there. Mr. Ty, rock and roll. Your unit for specific heat is, don't stress over it, but as grams per, joules per gram per degree Celsius, but I'm not really stressed over the unit for specific heat. Let's get down to number 8, do number 8, and then I'll set y'all free. All right, looking at number 8. Sample of chloroform is initially 25 degrees Celsius. What is its final temperature if 150 grams of chloroform absorbs 1 kilojoules of heat and the specific heat of chloroform is 0.96? Do we have a Q? What is it? Very good. Do I have an M? What is it? Very good. Do I have a CP? CP is specific heat. What is it? 0.96. Do I have a change in temperature? Nope. That's what I'm looking for. So it's going to be 1 divided by 150 times 0.96.
There's no more calculator.
Lots of calculators all over the place, sweetheart. I don't think so. 150 times 0.96 times 144 is not 1. Okay, 150 times 0.96 is going to be like 144. I agree. And then 144 times x equals 1. 144 times 144 is not equal 1. Whoa, would you know how I got what? Tell me what you're typing in your calculator. I'm listening to you. Okay, tell me what you're typing in your calculator. I didn't hear that part. 150 times 0.96.
And divided by 1.
Does that say divided by 1?
It's 1 divided by.
Okay. Would you rather have that many dollars or that many dollars? A or B? You understand how it's very, very different? Okay, don't let the fractions screw you up, guys. I heard a vote for 0.09, 0.0 what?
I got 6.94.
Sounds good to me. All right, now here's the deal. That's my change in temperature, right? I'll get you some more. That's my change in temperature. What did it say about your temperature in your question?
What is the final temperature?
Okay, so where did I start at?
25.
Oh man, I screwed something up too, guys. Why y'all let me screw something up? What did I screw up? Anybody see what I screwed up? Nope. I didn't screw up the grams. One of my numbers from my starting formula was wrong. Now CP's right. No, I didn't need to add 25 plus 273 because 273 is not a number in the question.
1.0.
What about it? 1.0 what?
Kilojoules.
So how many joules is that?
1,000.
Very good. So instead of 1 divided by, it should be 1,000 divided by. Sorry about that. All right. What's my starting temperature? And what am I going to do with 6.94 to get my answer? Well, who said anything about 273? I ain't say that. What? Stop. Does the question say anything about Kelvin? Very good. I know I'm going to increase my temperature by how much? So what am I going to do with that number? Okay, if I increased your money by $6, would I multiply your money times 6? What am I going to do? Yeah. What we got? Yep. And you don't need to go back and forth to Kelvin on these problems because all you would do is add 273 and then subtract 273, and that's
3.194.
31.94 what? Yeah. Make sure you put degrees Celsius because remember that's always a degree measurement. All right, guys. You got 6 more of those problems on the paper. You get that done, show it to me. If you get stuck, let me know. I'll put them on the board. Like I said, all my folks on this side of the room that didn't finish the lab yesterday, get that knocked out and turn it in and get some credit. I'm here for you. Go, go, go. I'm gonna edit this video real quick.